Next lecture. Um, this is the chapter 7. We'll talk about mixing. And I don't remember the 15, lecture 15. Okay. This is the lecture 15. So just let's recall just what we saw in the last lecture on Monday. I will denote, let's fix some notations first. This is, for me, this is will always be a measure preserving dynamical system. And we saw that a system is mixing if for every pair of sets we have that measure intersection converges to 0 as n goes to infinity. We saw some characterizations of this definition. We also saw some equivalences. We saw some examples. There is one thing that I forgot to mention that it's actually just a remark I forgot to mention, is that if f mi is mixing, then the function restricted to its support is topologically mixing. Remember that topologically mixing means that for every pair of open sets U and V, we have that there exists a natural number such that its intersection is non-empty of the pre-images. But this holds not only for one n, but for every n large enough. Okay? And this is actually very easy to prove. You just apply a definition. If the open sets have positive measure, then these will have positive measure, and then the measure for n large enough also has to be positive. So you can find n large enough such that the measure is positive, which implies that this intersection is not empty for n large enough. Okay, it's just this. Now we'll give another way to we'll weak this definition now. Okay, because in some contexts this definition here is too strong. So today we'll talk about weakly mixing measure preserving dynamical systems. Okay, so let's start with the definition. We say is weakly mixing if for every A and B the following holds. If instead of take the correlation functions, instead of say that the correlation functions converge to 0, we will say that the modulus of the correlation functions goes to 0 as n tends to infinity. Okay, and first remark is that this indeed is a weaker definition, but it's stronger than ergodicity. Indeed, we have the following sequences of implications, which is let me see here, this is the other remark here. Okay, this is the first remark, is that mixing implies weakly mixing, but weakly mixing implies ergodicity. And this is actually not too hard to see. Why? Because if the system is mixing, this implies that the correlation function goes to 0. So if let's prove this first, okay? Different colors. Call this A and B. To see why A is true, if I take two measurable subsets of M, then if I take the mean, I can write this as 1 over n, J0. Plus 1 over n, J and 0, and minus n0. Okay, where n0 is chosen such that this is smaller than epsilon. Okay, where is less than epsilon for n large enough. So this first term here, which is bounded, will go to 0 when n tends to infinity. Okay, so let me try to write with different colors. This goes to 0 because this is bounded. Okay, if the sum, this is a finite sum, so it's bounded. And this last one here, each one of these will be smaller than epsilon, so the overall everything here will be smaller than epsilon for n large enough. So this implies the weakly mixing. Now that A implies B, the weakly mixing implies ergodicity is done like this. I take a measurable, invariant measurable subset with positive measure. And then I just apply the definition of weakly mixing here. When I write this, this here will be just the measure of A because I'm taking this as a invariant subset. And by definition, this converges to 0. Okay, which implies that the measure of A square is measure of A, which implies by the fact that μ is positive, the measure of A is 1, and this implies ergodicity. Okay. So it's indeed weaker than mixing, but strong enough to get ergodicity. It's the weaker condition, the mixing. Okay, but just like mixing, this definition alone is not very useful to get examples it's not very useful to work with. So it's better to characterize. It's better to get other ways to characterize the weakly mixing property. So now we will state now we'll see some useful characterizations of this. Okay, useful characterizations of weakly mixing. The first one, which is going to take some time to prove, is the following: is that this is the first theorem. Okay, so suppose we have a measure preserving dynamical system. So the following are equivalent. Okay, now the first one is that the system is weakly mixing. B. Sorry, there is something that I forgot to say. Two things actually. The second, before I talk about it, my second remark is that just like when we got mixing, we could prove that a system is mixing if the definition holds for an algebra that generates the sigma algebra of subsets. We have the same thing here. If A is an algebra of subsets of M, such that the sigma algebra generated by A coincides with B, then the pair is weakly mixing. If the same definition holds for every subset of A. Okay. As n goes to infinity for every A and B in the algebra. Okay, this is the second remark. And here to enunciate to announce the theorem, I need a definition which maybe some of you have heard about it, but I will state anyway. Is that we say that a subset of natural numbers has zero density, if when I intersect this set with intervals of natural numbers, and then I take the I take the mean, this converts to 0 when n goes to infinity. Okay, an equivalent way to say this is that here this interval is, sorry, for me is okay. An equivalent way to say this is that this set has when I take the mean and I look at the characteristic function of this j, this converges to 0. This is an equivalent way to say the same thing. Now I will can finish stating the theorem. Maybe it's better to stay there. Let me erase this. Can I erase this? Yeah. Okay. Okay, let's start with our theorem. So let n be a measure preserved in dynamical system. Then the following are equivalent. First, the system is weakly mixing. The second condition is that for every A, B, there exists a subset of natural numbers with zero density. I will denote zero density sets as ZD, just easy denotation, with zero density, such that when I look at the sequence of correlations, okay, when I look at the sequence of correlations of these two subsets, and I look at the sequence of correlations where n is not in J, then this converges to the measure of B. Maybe it's better to put like this. Yeah. Just this means that except for a set of negligible natural numbers, the system is still mixing. Okay. But these natural numbers depends on the sets A, B that you consider. And the last condition is that now when I take the square, the mean of the square, this converges to 0 for every A, B measurable. Okay. Can I erase it? Okay. To prove this theorem, this is a theorem that hasn't. It's in the book by Viana, but one step of the proof he is left as an exercise. So we'll try to prove this theorem, each one of its steps. But for this, actually, this theorem will follow simply if I state the next real analysis lemma, which is actually it's almost the same thing, but with a sequence replace it holds for any sequence, not only a sequence of correlations. Okay, so let me state if I take B a bounded sequence of numbers, then the following are A, this converges to 0. B, there exists a set, a zero density set J such that the limit is 0, but when I take n in the set J, not in the set J, sorry. And for the last is that this converts to 0 as n is infinity. So it's clear why this theorem implies the last one. If I take the sequence an, the proof of this theorem is almost trivial, because if I take the sequence an to be right here, to be the sequence of correlations, then I'm done, right? Just applying this theorem. Now let's try to prove this. The idea of the proof, first I will try to prove that A is equivalent to B. The fact that, let's try to prove first that B implies A. I think maybe it's easier. Let's start with B implies A. Here we'll use the okay, so suppose there exists a sequence, there exists a set of zero density such that this holds. Has density and this is 0. So I'll just apply the definition. Here, I will denote by Sorry, there's something I'm forgetting. Okay. Okay, just to ease the notation, I will denote notation. For any interval of natural numbers, I would denote this as the intersection of J with an interval of 0 from to n. Okay, so as I'm assuming that J has zero density, this implies two things. Okay, this implies two things. The first one is that alpha J over n converges to 0. This just by definition, right? Here. This implies that for a given epsilon, I can take a capital N, which depends on epsilon, such that J over N is smaller than epsilon for every n big enough. And the second thing is that by hypothesis, this sequence converges to 0 when n is not in J. So I can assume that for the same, if you replace the capital N for n bigger enough, we can assume that if n is bigger than capital N and doesn't belong to J, then this is smaller than epsilon. Okay, is it clear what I'm doing here? Or AN is the sequence. Okay. So this 2 is by my hypothesis. This hypothesis. And 1 is just from the definition of the zero density set. Okay. Now, what is this sequence? This implies that that 1 over n, I can here write that sum as something like this. I can here write this as, I will take everyone that's in this set and sum. Then I will sum every term that's not in the intersection of this set. Okay, this is just taking every index, okay, that's in J, and every index that's not in J, and I dividing this as two sums. It's just like this. For example, if I have, for example, J equals to 0, 3, 4, and 6, then if I take, for example, then n equals to 6, then this sum will be A1 plus... first, I will sum everyone that's everyone that's indexed by elements that are not in this set. Okay. which is A1 plus A2 plus A5. And then I will sum everyone that up to index 6 that are indexed by that are indexed by terms that are not, sorry, that are in the set J this time. Okay. A3, A4, and A6. This is what I'm doing here. Okay, it's quite simple. But now I can estimate each one of these sums by 1 and 2, because if n is large enough, if j is in the set, in this intersection of j and the interval of from 0 to n, as I'm assuming that this is bounded, okay, this sequence is bounded, this will be less or equal than k. And then I sum everyone that's in the set J. But this is actually, this will be less or equal than K times the cardinality of this set. Okay? And here, we have the same thing, but here, everyone that's not the set J, this is smaller than epsilon, and then this will be this over here will be smaller than epsilon, and this I can choose, for example, this to be smaller than epsilon as well, and this will be smaller than 2 epsilon for n large enough. Okay, so this implies that this sum goes to 0. Now comes the hard part, which is to prove that that A implies B. So what's the idea? First, I try to separate the sequence, separate the terms of the sequence by their values. What I mean by this? For each k greater than 1, I will consider the set of natural numbers such that the term an, the modulus of the term an of the sequence is greater than 1 over k. Now the first remark is that Jk is a zero density set. Okay, because if I take the cardinality up to n of this set, as this is greater than 1 over k, okay? Sorry, there's something missing. Let me see. Oh, okay, sorry. Okay, so to prove that this is a zero density set, we have to choose our hypothesis. That first, this converges to 0 when n goes to infinity. Now to prove that this is a zero density set, as this sequence here, this converges to 0, okay, but each one of these AJs are bigger than 1 over k. Okay, but this in particular is bigger than 1 over n times the cardinality of these sets. Okay, because this AJKN is smaller than n for each n. Okay, it's just this. Now, if I let n go to infinity and I fix k, this is going to 0. So in particular, as this is positive, this is a non-negative number. This implies that this goes to 0 as well. So this proves that this is a zero density set. Okay. Is it clear what I did here? Okay. Have any questions? No. Okay. The second remark, this is the, let me see. Okay. The other remark is that, mark 2, is that each one of these sets are nested. And these sets are nested by definition. Okay. Now I'll try to do I'll try to do the following. I want to construct a set of zero density. So I use now each one of these sets to build my set of zero density. Yes, it can be released. Now I do the following construction. I will take a sequence of integers such that if n is greater than Lk, then this is smaller. This is smaller than 1 over k plus 1. This I can do this because if I fix k, and if I fix k, this is going to 0, and then I can take a L that depends on k, such that this is smaller than 1 over k plus 1. Okay? Just that's what I'm doing. So the set we are going to build is this one. I'll take the intersection of these guys over here. J0. And why this works? Because okay, so 2 claims I have to do. So I will write claim that J has zero density and this holds. Zero. If I prove this, prove the theorem. Let's not erase this. So if what I'm going to do, if I take this, the first remark I have to do is that this, I can rewrite this as the intersection of this set with this set over here. Okay, I didn't do anything. I just taking n larger than LK and then writing this as just the, sorry, there is an union. Okay, I didn't do anything. But remark that this set over here, this intersection, has to be contained in the union of the J1, J2, J3 up to Jk, because if I take a k plus 1, okay, if I take a k larger than, let's say, a k prime, larger than k, the intersection won't be, yes, the intersection is, of this set is 0. Okay? Because what I'm doing is that, let's say, I have my J here. 0, 1, 1, K, J. This set J, let me write another way. This set J, by definition, is the union of J0 with 0, L1, J1, intersection with L1, L2, union with JK, LK, yes, LK, LK plus 1. So when I intersect with the interval 0, LK, sorry, I think there is something missing here. Let's see. It's JK plus 1, so messed up here. It's J1, J2, and JK plus 1. This is my J, okay? But when I intersect this with the interval from 0 to LK, everything that comes after here is erased, and I only get everything up to here. Okay, because this I took these numbers LK to be an increasing number of natural numbers, and the interval that goes from 0 to LK, the intersection with all of them is exactly this interval here. The interval from the union of each one of these subsets. But observe that these subsets, the J1, J2, J3, they are all nested. So this is contained here. Yes, I want this. Okay. Because they are all nested and JK contains each one of these. So this guy right here is contained in this subset. And for the same reason, erase this. For the same reason, this guy here is contained in this set. Intersection with 0 to n. Okay. This implies that when I take the when I calculate the density, this will be smaller than 1 over n jk lk plus alpha jk plus 1 n. Okay, just by the definition of each one of these guys.
Something strange. The right thing it contains the left thing. Why do we need to unite them then?
Ah, you're saying that this contain here, right?
Vice versa.
Ah.
The left one is smaller, I think.
This is smaller.
Yeah. No, this is larger. Jk plus 1 contains jk
That's
and,
because
and,
okay.
and 0
the
n.
last right side is from LK to N.
Yes, yes, it's from LK to M, this left side.
And the left side.
And this doesn't intersect this set, okay?
It's because the right side you wrote 0 M.
So we don't want to write 0 n there, and just lk m.
The second line, the last interval is LK to N instead of 0 to N.
Should be, okay. Because, I mean, this set may be larger, but what I want here is just to estimate this guy in terms of these two guys which I already know them. Okay? It's just this.
Yeah,
that's what I'm doing.
Okay.
You'll see here what will happen.
But we don't need the first sound here.
This. Okay. Maybe we don't need this, but here everything that we're doing here, we just maybe I messed up here somehow, but here what we get in the ending is that this will be smaller than 1 over k plus 1 over k plus 1. Okay, because we already know these things. Okay. It's just this. Maybe we can talk later when the lecture finishes. But this implies that this goes to 0, and then this proves the claim. Okay, which the last thing that's left to do is just to prove this. But if n is larger than Lk and n is not in J, then of course n is not in Jk plus 1 for every k bigger than 1, which implies that an is smaller than k plus 1. Okay, so n not in J. So this proves that A implies B. Okay. And the last implication which I could do is A is equivalent to C. But I think I just left it as an exercise because I don't have much time. Yes. Okay, but the hint here to prove that A is equivalent to C is just observe that this limit is 0 for n not in J, and only if this is 0 for n in J. Okay, and this proves the form. Now with all this work done, I can give a useful characterization of weakly mixing systems. Let me state the following proposition, which is the measure observing dynamical system. The following are equivalent in the sense that one, F mu is weakly mixing. Two, the pair weakly mixing. And 3, this pair is irregular. Okay. And here, this map, what I mean by this map is just the map in the product. Where it's defining like this. You take fx in the first coordinate and fy in the second one. This is the map. And now we can apply apply this theorem, the theorem that I had wrote before, to this first proposition. So here I just prove 1 implies 2. Let me see. So now I try to prove 1 implies 2, 2 implies 3, and 3 implies 1. But I think the work that I will just do is 1 implies 2 because the rest of the proof is in the book by Viana. Okay. I want to prove 1 implies 2 because the book by Viana he doesn't do it explicitly. And this uses the theorem that we just proved. Okay, and we will do the following. I want to prove that this is weakly mixing. So let A be measurable subsets. So to prove that this is weakly mixing, I will apply this here. I will prove that for rectangles, let me state in another way. The claim is that there exists a set of natural numbers of zero density such that this limit here when n is not in J. Yes. this goes to 0. And to do this, we just basically apply the proposition. We can apply the proposition for A and B. So let me continue here. We continue here. For A and B, there is a let's call it J1 is zero density subset such that let's see, yes, this is such that this limit goes to 0. This converges to product when it's not in J1. And for C and D, there is a set J2 of 0 density such that this also holds. But here, when okay. But now I can just apply the definition. If I take now the set J, take the set J as the union. Just recall the finite union of 0 density sets is still a 0 density set. Okay. So J is 0 density. So when n goes to infinity and n is not in J, n is not in J. Let me state like this. This now this the measure of that set there. A C. Yes, I just here I just messed up the sets, but it's equivalent to what I want to prove. And here n. This will be the product of this. Okay, me C times the the measure of B intersection D. Okay, but as n goes to infinity and n is not in the set J, so in particular the n's are not in J1 and J2, so and in particular this goes to 0, this goes to 0, so this goes to 0. Here I actually there is no need to do for two sets. I could take only one, for example, but okay. So I can give you an example now. Let me erase this. As a corollary, this last proposition implies that the ergodic the rotations of the circle can't be weakly mixing. Okay, because when I take if I take any alpha, this may be rational or irrational. If let me write this. If I take any alpha real number and consider the rational notation in the circle, if this is weakly mixing, then the product would be weakly mixing. Okay, but the product of this thing, what is this map? This map is just translating the first coordinate by alpha and translating the second coordinate by alpha as well. But maybe you've heard this in this result in the book, that if you have a translation, a torus, then the translation is ergodic if and only if the pair which I'm summing, modulo 1, 1, the pair which I'm summing here is rationally independent. Okay, so what I mean by this is that there should exist an integer number so that n is 0. Sorry. If this holds, then n is 0. This is the definition of a rational independent real numbers. Okay, but obviously this can't be rational independent. It's just translation by same vector. So this is another way to see that this is a way to see that the rational rotation is not weakly mixing. Now I'll give a nice characterization of weakly mixing systems. Which uses spectral theory. And what I'm going to do is to apply a spectral theorem to give a nice characterization of weakly mixing systems that are invertible. So let me start some definitions. Okay. Here. Before this, I will just state a result. Which is a proposition which we saw for the mixing case in the last class. If you have a measure preserving dynamics of system, then the following are equivalent, that have me weakly mixing. This goes to, if I take here the the sequence of correlation functions, ej, goes to 0 as n infinity for every I psi in L2. Then this also holds. This is the L2 norm. This converges to 0 for every phi in L2. And the last one, the last condition is that the square goes to 0. L2. Okay, this is just a series of equivalents that we're going to need for the spectral characterization. But I won't prove this proposition, but the proof of this proposition is exactly the same as of the proposition that I did in the last class for mixing. Exactly the same. The only difference is that you have to take care with the means, but it's exactly the same. It's not hard. And I need this because now I want to talk about the spectrum of a weakly mixing system. And just definition for those of you that doesn't have the spectral theory course yet. We say that lambda an eigenvalue of of f if lambda is an eigenvalue eigenvalue of the Kopman operator. Which is natural operator defined in L2 which is just this operator here. Okay, which is equivalent to this. Okay, for some phi different from 0. Now the simple remark is that if this is a measure preserving dynamical system, then the Kopman operator is an isometry. This is just because it preserves the measure. Okay. The F preserves the measure, which is equivalent to, implies that if lambda is an eigenvalue, every eigenvalue has modulus 1. Okay? And Now we can state the following proposition. Sorry, the definition, which is, we say that F has continuous spectrum if the only eigenvalue of the system is 1. And the only eigenfunctions are the constant ones. Now we can state a beautiful theorem, beautiful result for me as like this. Which is the following theorem, that if we have a measure preserved uninvertible, if this is an invertible measure preserving dynamical system, then F is weakly mixing if and only if F has continuous spectrum. This is the theorem that I tried to prove in the last 13 minutes. Of course, this theorem is not for free. We have to use a canyon to get this theorem. And the theorem that we are going to apply, which I just apply at a lemma, it's a theorem that you are going to see in a spectral theory course, which is the spectral theorem. We'll need a canyon. And this, where is this? And the theorem I'm going to need is spectral theorem for unitary operators. Which is the following. Suppose U is a unitary operator in a Hilbert space H, in a complex Hilbert space. Then, for each element of my space, there exists a unique finite Borel measure mi phi, which depends on phi, such that the inner product is exactly this for every n integer number. So this is basically saying that I'm writing this. I can write the operator and apply this function. This can be written in terms of an integral, of a sum. And the second second part of this theorem is that if is a invertible measure preserving dynamical system, and F has continuous spectrum, then if this is 0, oh, sorry, there is, if phi is orthogonal to the constant function 1 in L2, this implies that phi has no atoms, which means that it gives measure 0 2 points. Okay, it's just I want to maintain this. Now I want to prove the theorem, the characterization, using this. Okay. So let's try to prove this. Now, proof of the first, we will suppose that my system is weakly mixing. I want to show that lambda is lambda equal 1 is the only eigenvalue of the system. So suppose that lambda is different from 1, and suppose that there exists a function and phi such that it's this holds. As I'm assuming that lambda is different from 1, then the integral, when I apply this, and I did this, this is the Koopman operator by definition. It's just this. Okay, but as I'm assuming that my system is measure preserving, this is 0. But this is exactly phi 1 minus lambda, the mu. And as I'm assuming that this is different from 1, this implies that this integral here is 0. Okay? Just this implies that it is 0. So I can, this in particular implies that when I take this, as I'm assuming that this is weakly mixing, this implies that this is 0. This is converging to 0. Okay, but this is also the same as this here is lambda phi, lambda to the j phi. But as this is measure preserving, the lambda has modulus 1, and then this implies that I can erase this, and this implies that this is 0, which implies that phi is 0. So we can have an eigenvalue of eigenvalue different from 1. And the last condition to prove that it has continuous spectrum is that the only eigenfunctions are constant. Okay? But if lambda is 1, then the condition that this is a fixed point implies that phi has to be constant, because weakly mixing implies ergodicity, and the only invariant functions are the constant ones. So this implies that it has continuous spectrum. Observe here that we didn't use the spectral theory here. The canyon part will be assuming that it has continuous spectrum. This is weakly mixing. I don't know what I want to erase. Okay, I will erase here. And I'll try. Now, assume f me has continuous spectrum. Okay, we need to show that it's weakly mixing. So we'll follow one of these characterizations. And the characterizations that we will prove is that this holds for every L2 function. So this to 0 every L2. I would suppose that this is 0. I can do this because if it's not 0, then I just take this function over here. Okay, this will be inner product of this will be 0, and then I can just erase this part. So what I try to prove is that this converges to 0 when n goes to infinity. By the spectral theorem, it's enough to prove that I will take the square here. Actually, sorry, I will use the second characterization. It's enough to prove that this one converge to 0 when n goes to infinity. Where phi is the spectral measure associated to the function phi. So I want to prove this. But now to prove this claim, now I can raise this. Prove this claim, I can rewrite that expression over there. As I'm taking the square here, I can rewrite this as the integral of this thing. times minus I dv. This is because this over here is just lambda I times lambda I modulus. Then I can just pass the modulus here. Sorry, it's lambda to the I. Okay, but when I take the modulus, I'm assuming that it has modulus 1, then it appears the minus sign. Okay? Now I do a change of coordinates here. I can't actually not, it's not necessary to rewrite this. Here I just replace the lambda by a tau. And now if I apply the Fubini's theorem, this will be this, the product of the measure, the tau. Okay, but this is actually this. Now, right? And then I can just take this integral inside. Yes. Okay. Now I assume that my pair of points, what I want to prove is that this converges to 0 almost everywhere. But this guy over here, I'm assuming that these are both numbers that are in the circle. If these guys are not equal, what I mean by this is that suppose that lambda is different from tau. If these guys are different, then 1 over n this is geometric series, and this I can here write it like this. Oh man, lambda, how? Here. This is bounded because these are a sequence of numbers that are contained in the circle, and this is in particular going to 0, so this is also going to 0. Okay. So what I proved is that for every lambda different than tau, this goes to 0. I can't guarantee this if lambda is equal to tau, but I'm assuming that my measure by the spectral theorem, I was assuming that this is an invertible measure preserved dynamical system, and this has continuous spectrum. I can guarantee that my measure has no atoms. So in particular, the product measure will give zero measure to the diagonal. What I mean by this is that we'll give zero measure to the set of the set of points that are equal. Okay. So this converges to 0 almost everywhere with respect to this measure. Okay. And this implies in particular that this converges to 0. Okay. And this finishes the proof. Okay. So this is everything that I wanted to show today. This basically finishes the weekly mixing part. And anyone has any questions? The proof, for example? Okay, so we'll finish it for today.